Next in the unit, we're going to learn the theorem of calculus. Some people call this part one, some people call this the first fundamental theorem of calculus, and then others might call the other part we're going to learn about later part two, or the second fundamental theorem of calculus. The two are very similar to each other, so I'm just going to call it the fundamental theorem of calculus, and then later we're going to learn about a specific case that's related to it. So we've talked already about definite integrals and indefinite integrals, but I just want to clear up any confusion by rewriting out the definitions for those in a slightly different way so we can make sure that they make sense. So a definite integral is the area under a curve on an interval. It has bounds, that's the interval, so it will give us a number. This is a specific instance. So we're saying what is the actual area under the curve on that specific interval. There's an actual number result. It has to be continuous on the interval. An indefinite integral is an antiderivative it will give us a family of functions. So here we're going to say the integral of f of x dx is the antiderivative plus c, because we don't know what the constant would have been on the end. That's why we say it gives us a family of functions, because it could be whatever the antiderivative is plus 0, or plus 1, plus 2, plus 3, plus 4. So it's a lot of different functions that would fit that situation. So if we're relating this back to what we've learned about derivatives, when we talked about derivatives, we said you can find the derivative at a specific point, and that's the slope at that specific point. Or you can find the derivative of an equation, which in itself is another equation that you could plug numbers into and find the slope. So here, the definite integral is a specific instance of the area under the curve. The indefinite integral gives you an equation or a whole family of equations that you could then plug numbers into to find the area underneath the curve. All right. So we're going to go ahead and do a couple examples of integrating the indefinite integrals. So that's finding the antiderivative. Those are two different ways of phrasing it. So integrating or finding the antiderivative. And then after that, I'm going to show you guys the fundamental theorem of calculus, and I think that it's not too much of a stretch to understand how we get there. So for example, we're going to do two examples first, and the instructions for each of these are just to integrate. So the first example, we're going to integrate 10x to the fourth minus 2 secant squared x dx. And if you want to use the property of integrals to split those into two different pieces and to take the coefficients and move them to the front, you can do that. But we can also do it without splitting them apart. We can do it just the way it looks right now. So I would say I'm going to add 1 to the exponent and then divide by that number. So 10 divided by 5 is 2, and that was x to the 5th, minus, that coefficient is going to stay with us, and then the antiderivative of secant squared is tan. And then we have to include the plus c. So we would say that that would be the integral of the function, or that we took the antiderivative. All right, example 2, we're going to say cos theta over sine squared theta d theta. And when we look at this, it looks like a quotient rule, but remember, we said that the quotient rule was a process of taking the derivative, and the answer didn't look like a quotient. Well, actually it did, but the answer didn't, but it involved more than just a fraction. So when we do the antiderivative, we can't use the quotient rule because that's taking derivatives, not antiderivatives. So we have to rewrite this problem so that there's no quotient involved. So what I'm going to do is I'm going to start thinking about how I could split this apart and use the different trig identities to figure out what this problem really should have been. So what I'm going to do is I'm going to think of this as cos theta over sine theta. And then since it was sine squared on the bottom, I'm going to say that that's multiplied by 1 over sine. So all I did is I kind of split the problem apart. Now I know that cos over sine is cotangent. So now I've taken something that was a fraction and I've written it as something that is not a fraction. And I know that 1 over sine theta is cosecant theta. And it looks like that might be a problem as well, just because this now looks like a product rule and we can't do that with antiderivatives. However, cotangent theta cosecant theta is an antiderivative of something. So if you look back at your notes, you'll notice that is actually the function whose antiderivative is negative cosecant theta. And then we're going to, of course, add the plus c on the end. Okay, so that's just integrating, that's working with indefinite integrals. Now we're going to go back and work with definite integrals, and in previous days of this unit, the only way that we could possibly work with a definite integral was to use Riemann sums. That was where we said a definite integral up here. I can go ahead and write an example of this. This would be a to b of f of x dx. And so we said, yep, we're finding the area underneath the curve. I have to figure out how many subintervals I want to use, and then I need to use rectangles with left endpoints or right endpoints or midpoints, or I could use trapezoids, and my answer was going to be approximate. My answers would be better if I used more subintervals, but I could never get an exact answer. Today we're going to look at how we can get the definite integral to give us an exact answer using calculus instead of shapes. So that's what we're doing. That's what the fundamental theorem of calculus is based on. So here's the fundamental theorem of calculus. The fundamental theorem says if we're taking an integral and we're evaluating it from a to b, then that is really the antiderivative evaluated from a to b. So this is the notation that we use. This is the antiderivative. That's why I used lowercase f over here with the integral and capital F representing the antiderivative. And the way that you evaluate using these numbers is you do the antiderivative evaluated at b minus the antiderivative evaluated at a. So typically we know that the smaller number is on bottom and the bigger number is on top. And so we just do f of the bigger number minus f of the smaller number and get our result. It is possible for them to have flipped those numbers and have the bigger number on bottom and the smaller number on top, and we know that just gives us a negative answer. All right, so now we're going to go ahead and use the fundamental theorem of calculus to evaluate some examples. So just remember, this is kind of like what we did with derivatives, where the indefinite integral gives us more general results. It gives us an equation as a result. The definite integral is going to give us a specific result, a number answer. So here, when we see the instructions, they're going to tell us to evaluate this, because when you evaluate things, you can get a specific answer. So this time, we're going to go ahead and we're finally going to look at that parabola question that we did. We said the area from 0 to 1 of x squared dx, and we've looked at this problem using rectangles and trapezoids and right endpoints and left endpoints. We've done it a bunch of times, and we knew the answer was 1/3, and now we get to find out why. So first we're going to go ahead and integrate this. I have 2 plus 1 is 3, so I'm going to divide it by 3. And so that means the antiderivative was 1/3 times x to the third. And that 1/3 is being evaluated from 0 to 1. So now, using the fundamental theorem of calculus, I'm going to say that's actually 1/3 times 1 to the third power minus 1/3 times 0 to the third power. And this part would zero out, that would be nothing. And so we have 1/3 times 1 to the third power, which is just 1/3. And that is how you get the exact answer. Okay, let's look at another example. We're going to find the integral from -2 to 1 of x to the third plus 1 dx. So I'm going to add 1 here, that's 4, divided by 4. So we have 1/4 x to the fourth plus 1x, and that's being evaluated from -2 to 1. And you'll notice the big difference here is that we are using almost like the parent antiderivative, where we don't have the plus c on the end. If you guys noticed that, we didn't worry about the plus c. So that's one of the nice things about definite integrals, is you don't need to put that plus c on the end. You don't have to solve for it unless they have given you the information to do that. So here I'm going to go ahead and plug in the 1 first, then I'll plug in the -2. So I've got 1/4 times 1 to the fourth plus 1 times 1 minus 1/4 times -2 to the fourth plus 1 times -2. And then I can go ahead and simplify this a little bit. 1/4 times 1 is just 1/4. 1/4 plus 1 is 5/4. -2 to the fourth would be positive 16. 16 over 4 is 4. 4 minus 2 is 2. So we're subtracting off 2. And yes, this is a fair question without a calculator. You should be able to do this by hand or in your head. You can, multiply some stuff on paper if you need to. So 1 and 1/4 minus 2 is -3/4. And so that's the area underneath that curve. Okay, number 5. We're going to do the integral from -1 to 3 of 1 over x squared dx. And sometimes, I'm going to have you guys write this in an alternate form. Sometimes I've seen people write this as -1 to 3 of dx over x squared. I don't like it written like that because I don't think you can see that it is the height of the rectangle multiplied by the width of the rectangle. But mathematically speaking, yes, you could think of those as being multiplied together. So if you ever see it like that, you can split it apart if it makes you more comfortable. So when I look at this problem, most people just kind of get started as per usual. However, you have to look and see that x cannot equal 0, and 0 is on this interval. And so this, we would say, does not exist because 1 over x squared is not continuous on the interval. So it's not continuous on the interval because there's actually a vertical asymptote at 0. So x equals 0 would be a problem there, so we cannot evaluate that integral. Okay, we've got one more example. So this one we're going to evaluate the integral from 0 to pi fourths of secant squared x dx. So the antiderivative of secant squared is tan, so that's going to be tan x evaluated from 0 to pi fourths. And so we're going to say tan of pi fourths minus tan of 0. Tan of pi fourths, we have to think about the unit circle at pi fourths, and that's the y-coordinate divided by the x-coordinate. And so that's root 2 over 2 divided by root 2 over 2, which is just 1. And then tan of 0 would be the y-coordinate divided by the x-coordinate. That's 0 divided by 1, which is just 0. And so 1 minus 0 is 1.